Our sixth problem-solving strategy is to solve a simpler problem. This is appropriate when the problem involves complicated computations, or very large or very small numbers, or if a direct solution is too complex, or you want to gain better understanding of the problem, or if the problem just involves a large array or diagram. So in our example, it would qualify based on these last two. To gain a better understanding of the problem, we can start solving a simpler problem, and it would also be a pretty large diagram if we tried to make a sketch to help us out. A schoolroom has 13 different desks and 13 different chairs, and you want to arrange the desks and chairs so that each desk has a chair with it. How many arrangements are possible? So for this problem, we're assuming that basically each desk has a number and each chair has a number, and they're all different, or maybe they're all different colors, something like that, but they are distinguishable, and therefore it's different pairings based on which desk goes with which chair. So if there's 13 desks and 13 chairs, we could try setting it up, but that is going to be rather complicated. So let's take a smaller number. What if there's 3 of each? 3 desks and 3 chairs. So we have desk 1, desk 2, and desk 3. Desk 1 could get either any of the 3 chairs, chair 1, chair 2, or chair 3. If it gets chair 1, desk 2 could get chair 2, and desk 3 could get chair 3, or we could flip those. Desk 2 could get chair 3, and desk 3 could get chair 2. Similarly, if we gave chair 2 to desk 1, then desk 2 could get chair 1 or chair 3, and desk 3 would get the other. So if 1 and 2 are out, then desk 3 would get chair 3, or if 2 and 3 are out, desk 3 would get chair 1. Or if we gave chair 3 to desk 1, we could then give chair 1 to the second desk and chair 2 to the third desk, or we could flip those and give chair 2 and chair 1. So we have a couple different options here. We have chair 1, chair 2, chair 3, or chair 1, chair 3, chair 2. So there's 2 options there, 2 options there, and 2 options there. If we go even simpler, and just start with 2 desks and 2 chairs, we would have chair 1 and chair 2, or chair 2 and chair 1. So there's only 2 options here. Here we have 6 options. If we tried building this up and adding in a 4th desk, we can get all of this happens for each desk that we can assign, or each chair we can assign to our fourth desk. So we can assign chair 4 with all of that happening. Or chair 3, where we just replace all the 3s with 4 over here. Or chair 2, where we replace all the 2s with a 4, and so on. So there would be, since there's now a fourth chair, all of these happen for each of the 4 different scenarios. It's pretty easy to see if you do a tree diagram. You start listing it out. So this happens 4 times total. So if we add in the fourth desk, it will be 6 times 4. And if we added in a fifth desk, all of that would happen for each of the 5 times. So it would be times 5. And this starts to make a little bit more sense. Instead of writing 6 options, we write 3 times 2. There's 3 different 2s here. If we added in the fifth desk, that all of that would happen for each of the 5 different chairs that desk 5 could get. If we added in the sixth desk, each of that could happen for each of the 6 different chairs that the 6th desk would get, and so on until we get up to our 13th desk. So for this, our answer is going to be 13 times 12 times 11 times 10. 9, 8, 7, 6, 5, 4, 3, 2. You can actually include the 1. So it's over 6 billion different ways that could happen.